Welcome to ECSE FYP. My name is Qi Yuan.
My name is Yuan Xing.
My name is Wong.
We are going to introduce to you Smart Solar Concentrator, an efficient solar hot water system for small residences.
Australia has the highest average solar radiation per square meter in the world. This abundant renewable energy is used mainly in small-scale residential applications, such as water heating, which accounts for 25% of household energy. Traditionally, a solar panel is mounted on a stationary support, which compromise productivity and is require optimal angles. To compensate for this, we aspire to build an autonomous solar tracking system with dual axis control to ensure the sun's passage through the skies is traced with high precision for the longest periods of the day. Our smart solar system is designed to be portable and requires minimal setup from users, which are some of many key features. Here is a demonstration of how the system is set up when the product is first purchased. Once the client decided where to park his system, the dish should face either the east or the west. Next, the sun tracker should be adjusted so that it is situated higher than the dish. These steps are only required when the system is first purchased. User can set water temperatures, date and time on the friendly user interface. On the home screens, user can see date, time, as well as monitor the environmental and hot water temperatures and flow rate. By pushing the setting button on the bottom left, a setting screen shows up. Here, user can adjust date, time, and his desirable temperature. One of the most important components of our system is a reflector. The reflector is made of parabolic dish whose focal plane is 7 cm away from the dish and 15 cm wide. The solar dish is paneled with acrylic mirrors, which he prefers in many customized applications due to its high flexibility and durability. After a thorough assessment of 3 candidates for patent, a leaf-like design has been selected. The unit plays a critical role in increasing energy efficiency. The collector was made in cylindrical shape. It was chosen for low ratio of lost sun rays to trap sun rays. Furthermore, at certain absorptivity, flux distribution in cylindrical cavity is relatively uniform. The design length of the cylinder wound around by copper pipe is 408 mm. It requires 68 windings, or an equivalent of 28 meters of copper pipe. The copper pipe was then encapsulated by 2 sheets of aluminum sheets. A layer of 20 mm thick insulator of glass wool is sandwiched in between. To increase thermal absorptivity, black paint was applied on the copper pipe winding as well as the bottom of the receiver cavity.
The driving mechanism for the dish consists of 2 motors. A linear actuator is used to control the pitch angle of the dish. The device is well lubricated to provide a smooth movement. It operates at 12 volts and can support maximum load of 2,500 Newton at a speed of 30 mm per second. An internal reed switch allowed feedback to the piezo controller to accurately retract or extend the actuator to achieve desirable pitch angle. The pitch angle of the dish is ranged from 0 to 57 degrees referred to the ground. A limitation of this switch is bouncing. It compromises the accuracy of pitch control if this problem is not resolved. We have overcome this difficulty with proper debouncing technique implemented on the software. The yaw movement of the dish is controlled by a high-precision stepper motor. It works at 12 volts and driven by an H-bridge. The stepper motor provides a precision of 1.8 degrees per step. By using a gearbox with a ratio of 50:1, the dish is able to rotate 0.017 degrees per step. The stepper motor allows the dish to swing from east to west and vice versa. Home position for yaw movement is implemented with a pair of magnet and Hall effect sensor circuitry. Homing is executed every morning to eliminate accumulated errors. To dynamically trace the sunlight, a light sensing system called sun tracker is built. The sun tracker consists of 4 light-dependent resistors arranged in 4 quadrants. The wall separating 4 compartments are painted in black to isolate light sensed by each LDR. The sun tracker determines its yaw angle first by comparing the sum of 2 left side LDR readings and the sum of 2 right side LDR readings, and then rotates 1 degree towards the higher value set. Then the sun tracker used the same method to adjust its pitch angle by comparing the sum of 2 upper LDR's readings and the sum of 2 lower LDR readings instead. The sun tracker keeps repeating the above steps until the sum of left and right-hand side LDR readings are identical, and the sum of upper and lower side LDR readings are identical as well. The sun tracker always aligns itself with the sun by regularly tracking and updating its sun position at a frequency of 10 Hz. If the light sensor was mounted on the dish would continuously rotate and consume a lot of energy, especially when it's accelerating. Our solution is to design the sun tracker as a standalone system and update the dish's position every 5 minutes with the last sun tracker's position. Piping network consists of silicon tubing to minimize heat loss, and it can stand high water temperature up to 300 degrees. The tubing was carefully organized to impede the dish movement in 2 axes. The tubing network allows water to circulate from an insulated water tank to the collector to be heated up and returned to the tank. The water tank has a capacity of 25 liters of water and equipped it with pressure relief valve to prevent pressure building up as water has been heated up.
The circuitry was designed using RTM Designer. In RTM Designer, as you can see here, some components can be found in genetic libraries, and some need being created from scratch. For example, here an LM35 temperature sensor is being created. To overcome the limited number of GPIO pins, we utilized a control bus and a data bus to regulate communication between PSOC and all peripherals in a productive manner. The circuit also includes a power-saving scheme for stepper motor. When it remains stationary, the stepper motor is only fed with 5 volts instead of 12 volts to withstand the wind load. It guarantees that the system is stable under windy environment. Additionally, this implementation cuts down overall power consumptions of the system. After 8 revisions, including testing functionality of our circuit on prototype board, a PCB was designed. At the heart of our design is the Programmable System on Chip, or PSOC. It was chosen for its low cost and flexibility. PSOC is allowed to interface with the outside world through a wide range of pre-verified special functions, such as PWM, debouncer, and ADC, that can be internally connected with external pins. Due to the complexity of the program, we developed a flowchart and continuously refined it throughout the project. It provided our team an effective means of communication and hence facilitated our collaboration. Additionally, we hold regular meetings to revise our code, especially to establish convention on naming variables. Therefore, although we contribute different functions to the final program, our code were compatible with each other.
During this project, we have learned a variety of skills that help us become employable. We learned how to design PCB with Ultimate Designer by ourselves, with regular consultation with our supervisor.
We also enhance our mechanical design skill with SolidWorks by working closely with many senior support staffs. We learn how parts of complex geometry are machined in practice.
The system we designed satisfied our goals in terms of performance and aesthetics. Our design paved the way for further developments in generating power such as electricity.